Hi everyone, welcome to Tenerife Summer Sessions. I am Ramakrishna Pittu and today I'll be presenting on AI-powered observability from reactive to predictive. Modern enterprises produce enormous amounts of operational data every second. Traditional monitoring approaches are no longer enough because by the time alerts appear, the users may already be facing issues. Today, I'll explain how AI transforms database observability from simply reacting to failures toward predicting and preventing them. I am Ramakrishna Pittu, working as a senior systems development engineer at Google. I have around 20 years of experience exclusively on database platforms, where I work on large-scale database infrastructure, cloud systems, automation frameworks, and database reliability. Over the years, I have worked with enterprise database platforms, did large-scale cloud migrations, worked on different automation frameworks, and handled large-scale production database infrastructure consists of hundreds of database servers. This experience motivated my interest in applying artificial intelligence to improve operational performance and then reliability. Today's discussion focuses on how AI changes the way we monitor databases. We'll go through current monitoring approaches challenges, AI technologies, practical AI observability architecture, implementation guidelines, and future directions. The observability challenge. Cloud-native databases continuously generates logs, metrics, traces, events, and performance telemetry at a massive scale. It's not about collecting the data, but to understand what matters. That is the most important thing. That's where the traditional monitoring systems are failing. AI changes everything. Instead of reacting to incidents, AI enables engineering teams to anticipate failures, identify emerging risks, and automate responses before service disruption occurs. By continuously learning from historical patterns and operational data, AI models grow more accurate over time, dramatically reducing mean time to resolution and cutting operational costs through fewer escalations, faster root cause analysis, and intelligence automation. The biggest shift here is from reactive operations to predictive operations. The traditional monitoring system says something already failed, whereas AI says, I see a pattern that suggests something is likely going to fail in an hour or in few hours. That's the difference. Think of AI as like weather prediction system, where instead of waiting for rain to fall, weather prediction systems basically predict based on wind, temperature, humidity, and calculate when rain is going to happen and then forecast accordingly. Similarly, AI does the same thing for us in the observability. The evolution of database monitoring. So there are few stages. Initially, in the first stage, we used to collect infrastructure metrics like CPU, memory, storage, and then create manual dashboards. And on top of these values, basically we set static thresholds. Whenever the threshold crosses, we used to receive alerts. In the second stage, we started aggregating logs from different applications and putting it in a central location for easy analysis. Third phase is distribution tracing. Microservices era visualize requests across services and dependencies. Like nowadays, applications can have a dozen to 100 microservices, where each microservices performs some operation. For example, if user clicks buy, it goes through basically authentication, payment, inventory, suggestions, and then to database. So the chain of that particular microservice basically is recorded, and then everything like in that process gets recorded for easy troubleshooting. Now we are in a fourth stage, AI observability, where continuous learning, pattern detection, and forecasting and automated remediation happens in AI observability. Observability has shifted from reactive monitoring toward intelligent operational prediction. Challenges in traditional monitoring: alert fatigue. Static thresholds generate excessive notifications, eroding engineer confidence. For example, if engineering teams receives 100k errors in a day, then eventually most of them are being ignored. Dynamic environments: Kubernetes, auto-scaling, and container churn make static rules obsolete. Telemetry diversity. We have so much data in different forms like metrics from Prometheus, logs from Elastic, traces from OpenTelemetry, SQL plans and replication stats from SQL Server. And these are all in different formats. That is another challenge. No predictive power. Basically, with all this data, traditional monitoring systems, they won't predict what is going to happen in next 1 hour or in the near future. They just work on the thresholds we create. Once the threshold is reached, it sends alerts or creates instance. These are the challenges we are facing in traditional monitoring. AI technologies driving predictive observability. Several complementary AI techniques work together to transform database monitoring into a proactive intelligence capability. These techniques span machine learning for anomaly detection, natural language processing for log analysis, and deep learning for time series forecasting. Each address a distinct layer of observability stack to catch issues before they become issues or outages. Core AI techniques: machine learning learns normal behavior from history, detects subtle deviations without manual thresholds. Anomaly detection flags abnormal query patterns, latency spikes, and replication delays before they escalate. NLP log analysis groups similar error messages automatically, surfacing recurring issues at a scale. Let's say like a log file has 100k lines, and not 100k lines are like distinct errors, right? There may be like errors repeating continuously. So NLP log analysis, what it does is like it analyzes those logs and then group by error message and provides like maybe 50 to 100 or 200 unique errors present in that log. Time series forecasting predict future resource utilization to enable proactive scaling and capacity planning. If a database requires 5 GB for a day operations, then basically AI automatically calculates how much storage is needed, and accordingly like the automatic scaling happens once we implement full AI observability techniques. Graph analytics and reinforcement learning. Together, these techniques provide continuous operational intelligence that far exceeds conventional monitoring, correlating events across system and learning from every instance. Graph analytics maps the blast radius during failures instantly, revealing which downstream services and databases are at risk, while reinforcement learning continuously refines remediation playbooks based on the. Basically, AI knows the regular workflow and the sequence of events basically in the microservices. It knows like the dependency of the entire system, and if something fails at one point, it maps where exactly this issue is coming from, and then identifies the root cause and then summarizes and then gives us. Traditional monitoring systems, they won't provide this kind of information. Reinforcement learning, basically this technique learns from the past instance improvements, continuously do the improvements to the automatic response. AI powered observability architecture. This is a closed loop architecture where telemetry ingests the metrics and then ML predicts based on the data provided, and then whatever the feature engineering adds to resolve those issues, to respond to those instances, then the automated remediation will go and fix that instant. So this closed loop design enables continuous monitoring, predictions, diagnosis, and response, all without manual intervention for routine issues. Telemetry ingestion at scale. So this is a crucial step in AI observability architecture. So the data, the quality of data we provide is the plays vital role in AI observability reliability. What gets collected? database engine and OS metrics, centralized application and infrastructure logs, distributed traces across microservices, storage, replication, and container events. Streaming platform process telemetry in real time, enabling immediate analysis rather than batch processing. Practical ML techniques. Clustering. These are some of the ML techniques we use in database observability. One is clustering, where we group similar operational behavior surfaces recurring workload patterns. Classification distinguishes healthy or unhealthy states, prioritize alerts by risk. Regression forecast latency, storage, throughput, and replication lag. Deep learning analyzes complex multi-stream relationships invisible to traditional statistics. Ensemble models combine multiple procedures to improve accuracy and reduce false positive. These are 5 different techniques. Basically, if you think of like in a practical world example, consulting 5 different doctors and then getting the best opinion for the treatment. Intelligent event correlation. During single incident, distributed systems generate thousands of independent alerts. AI automatically correlates logs, metrics, events, traces, deployments, and config changes, then generates a concise narrative explaining the root cause. Deployment happened. For example, a deployment happened, configuration changed, and query performance degraded, and then database is responding slow. That's the user is complaining, database is slow. So traditional monitoring system, basically each layer produces hundreds of alerts. The database engineering team or admin team has to go through those alerts. They have to see like what exactly happened, and they have to correlate manually like which layer to which layer this issue spanned, and then come up with the theory that this could have happened. But whereas AI, what it says like deployment X happened and that caused database latency. Simple. Basically, this intelligence correlation dramatically reduces mean time to identify, enabling teams to focus on remediation efforts on the actual source of failure rather than chasing false positive or cascading symptoms. From noise to root cause. Traditional approach, hundreds of unrelated alerts presented individually. Engineers manually determine which events present the real problem. In this diagram, if you see, the problem is increased query latency. So what are different stacks? Basically storage, contention, maybe that causes slow disk I/O, network, congestion, packet drop, resource exhaustion, memory leak, or CPU bound, deployment, inefficient scaling, microconfiguration, misconfiguration. So traditional approach, as I explained earlier, like storage layer produces some alerts, network produces some alerts, resource related will get alerts, deployment related we don't get alerts basically, but it is recorded. So these alerts, basically DB team, admin team, they have to go through like what has changed or why this alert is coming and what is causing. They have to analyze storage first and then see like if storage wise everything is good or not, and then go to network and then see, and then resource wise they'll check CPU, memory leaks or anything, and then come to a conclusion. It takes a lot of time. Sometimes it's like it takes more than expected time to identify what caused this issue. Whereas AI, because it knows the dependency graph, so it understands it. It basically correlates the sequence of actions and then come up with the root cause. Dependency graph traces relationships across services, databases, storage, and network. AI identifies the sequence of contributing events, not just isolated symptoms. Automated proactive remediation. First step is AI detect risk. Predictive model flags emerging performance issue with high confidence. Orchestration triggers. Kubernetes operators, ISC pipelines or workflow engines execute response. Action taken, scale resources, rebalance workloads or restart services or expand storage. Human escalation, only situations requiring expert judgment are escalated to engineers. AI assists database administrator handling repetitive tasks while preserving human oversight for complex decisions. Basically, what it says is like AI does everything for admins for the regular operational work. At the same time, like there will be like human oversight according on this operations. Implementation best practices. Start with quality telemetry. Basically, the data is more important. The metrics we provide, if we provide good metrics, then AI does good job. If we provide useless metrics, then AI does good job. Basically, garbage goes in, garbage comes out, like that simple example. Start with quality telemetry. Accurate, complete, consistently formatted logs and metrics are the foundation. Define measurable objects. Select clear operational goals before selecting ML models or automation workflows. Start simple, then expand. Begin with anomaly detection and correlation before adding advanced prediction. Update models with production data as workload and infrastructures are evolving. Validate before automating. Stage deployments carefully before enabling automation redemption. Autonomous remediation in production. Cross-team collaboration is essential. So when we say database observability, it's not only database admins work. It spans across multiple teams: database admins, DevOps engineers, SREs, data scientists, and software developers. Successful observability initiatives require alignment across all these teams. Observability must address both the operational and business requirements, not just technical metrics. The future. Autonomous operational intelligence. Observability is evolving beyond prediction towards self-managing infrastructure, where AI doesn't just alert, it understands, explains, and acts. Today it recommends, tomorrow it acts. Autonomous operational intelligence will empower systems to self-heal, self-optimize, and self-configure, closing the loop between detection and resolution without human intervention, while in meaningful auditability and governance. Future directions. Foundation models. Explain incidents in natural language and generate automated remediation runbooks dynamically. Digital twins. Simulate infrastructure changes in a virtual replica before production environments. Basically, whatever the changes we want to perform, we will apply them in virtual replica and then validate and then make sure that everything is working as expected. Federated learning. Predictive observability for distributed edge infrastructure while preserving data privacy. Organizations work together to achieve this goal without basically sharing sensitive information. Explainable AI. Clear descriptions of why models generated specific predictions, building operational trust. So the strategic shift in database observability is basically reactive to predictive. This transition is not only a technological advancement, it is a strategic shift toward proactive operations. Organizations adopting AI-powered observability will be equipped to manage modern cloud-native infrastructure and deliver reliable digital services. What are the advantages? Reactive to predictive. Reduced operational complexity. It eventually reduces the escalations and then operational cost of managing the service. Faster incident response. Basically, we resolve the issues quickly. Improved service reliability. That translates to customer satisfaction. Stronger system resilience. Basically, system reliability will be improved. This is the strategic shift every organization is moving towards, from traditional monitoring approaches to AI observability methods. Key takeaways. AI transforms observability from static thresholds to continuous learning, anomaly detection, and forecasting. Closed loop automation. Prediction, orchestration enables remediation before user experience impact. Start simple, scale deliberately. Quality telemetry and clear objectives are prerequisites for AI success. The future is autonomous. Foundation models, digital twins, and multi-agent systems will define next-gen operations. These are few topics I wanted to cover on AI observability. Thank you so much. I hope you enjoyed this session.